So for the time complexity of binary search, we of course start with the recurrence relation. So binary search, when applied to a list of size n, would call binary search for a list of size n over 2, since we have the list. And then we add a constant runtime for the constant operations happening outside the recursive call, which are the comparisons to check for the base case and then the computations for the middle element. So, and then for the base case, it will be just of constant time. So let's apply the substitution method for this for this recurrence relation to get a closed form solution. So our starting point, t of n is equal to t of n over 2 plus some constant. Now when we expand t of n over 2, we get t of n over 4 plus c. Then we just combine the like terms, and then we expand the tn over something term again. So t of n over 4 is equal to t of n over 8 plus c. And then that results to t of n over 8 plus 3c in total. And then if we expand this term again, we get t of n over 6 plus 4. And then when we expand this again, we get t of n over 32 plus 5. Now, notice that the t of n term, or t of n over something term, is always divided by something that's a power of 2. And if you notice that the coefficient of C1 is actually that specific power of 2, which means that 32 is 2 to the 5, 16 is 2 to the 4, 8 is 2 to the 3, etc. So we can rewrite this as this expression over here. So t of n over 2 to the k plus kc1 is our t of n. Now, uh, since we know that when we have a t of 1, when t is equal or less than or equal to 1, it simplifies to a constant. Oops, sorry about that. We can substitute, we can let n be equal to 2k so that our expression here in the middle will be equal to 1. Then solving for k, that means k will be equal to the log of n. So plugging it into the equation, if n is equal to 2 to the k, the 2 to the k term here becomes n. And then our k term here becomes c1 log of n. Then this one is just a constant, and this one is retained over here. So now if we apply our rules for asymptotic notation, the big O of t of n is actually just log of n. So this is a better linear search time. This is better than the linear search time, which is O of n. I don't think I need to show that log of n is smaller than n.